Okay, good morning, everybody. It's a great pleasure to welcome GONCALO ARAUJO-REGADO. Yeah, I know, I had one Araujo in our group. He received his PhD from University of Cambridge in 2023. I think since then you moved to Okinawa, working with Philip Kern on all the interesting things for PhD as well. He worked on the relation between canonical quantum gravity and horizons. So today we will hear something about an edgy topic.
Yeah.
Edge modes, so please welcome.
Thank you very much for the kind introduction. Very happy to be here discussing this topic to this audience. So I'm going to try to give more of an overview talk about the edge mode program that we've been carrying out in Okinawa. So I'll present a series of results and our current understanding of what edge modes are. So I'll start first with the plan of the talk. First, I'm going to start with the motivation of why we should care about edge modes, what edge modes are, what the kind of physical questions are that we are interested in. And then the talk is going to be split into 3 parts. First, I'm going to start with the classical setup of Maxwell theory, in which we can do everything in the continuum. And I'm going to give some intuition for how to build edge modes from there. And I'm going to discuss some concepts that will appear later on as well, such as the notion of a subregional Goldstone mode, and also the concept of corner symmetries. And then the main part of the talk is going to be part 3, where we're going to go to the quantum level, but on the lattice. And we're going to quantize these edge modes, and there's going to be a lot of connection with the quantum reference frame formalism at this point. And a lot of things you may see will be familiar to you, hopefully. And in particular, the crucial part of the talk will be this 3B, relational subregional algebras, and the notion of different notions of entanglement, entropy, and a hierarchy of algebras. And I think that's going to be quite maybe the main punchline of the talk. And then I'm going to, if I have time, I'm going to discuss some problems in going to the continuum at the quantum level, and some ideas that we've been having. But this is still work in progress. Parts 2 and 3 is work that's already finished. And then I'm going to conclude with some future directions. And you can stop me at any point for questions. So let's start with the motivation. The main motivation is that we want to be able to describe subregions in gauge theories. So the standard model is based on gauge theories. We are built from gauge theories, and we have access only to a subregion of the universe. So imagine some sort of partial Cauchy slice sigma with some boundary, like the walls of this room. And this is the causal development of that region. And if we only have access to observables to this region, we want to be able to describe this in a gauge invariant way. So edge modes will, as I'm going to try to explain, are going to be crucial to be able to perform this task. A related question is, what does it mean? What is the meaning of entanglement entropy in gauge theory? So when we talk about entanglement entropy, we trace over some degrees of freedom that we don't care about, and we compute the entanglement entropy of the reduced density matrix on the, in this case, the subsystem is a subregion. What is the meaning of this entanglement entropy? There's a whole very long literature of people trying to address this problem, and there's many notions of entanglement entropy that give different answers. So there's a bit of a whole zoo of notions of entanglement entropy, and the edge modes will help us put some order into this. And it will also help us understand what the entanglement is actually measuring. So as I said, the edge modes are going to be crucial for tackling these kind of questions. And one of the things you should take away from this talk is that these edge modes are nothing but reference frames for the gauge group on the corner. So when I say corner, I always mean this partial sigma rim surface here, the yellow line. So they parametrize the orbit of the gauge group at this corner. And that's really the point where if you're not careful, you would break the gauge symmetry, and you don't want to do that. So the edge modes are going to help us do this in a consistent way. And there's a long-standing question of, are these edge modes new degrees of freedom that we just add by hand, or they're already there? And there's all sorts of schools of thought on this. I'm in the Okinawa school of thought, so these are not new degrees of freedom. These degrees of freedom are already there in the global theory. They're built from the global degrees of freedom. And just from the subregion perspective, they may or may not look like new degrees of freedom. But they're already degrees of freedom that are already present in the global theory. And this, having this framework of these edge modes and keeping track of where they come from is going to give us new insights about entanglement, as I said, in gauge theories. Also, crucially and relatedly, subregional algebras, what do they mean? And also something I will not touch that much on this talk, some connection with soft physics. So there's going to be very strong structural similarities between the edge modes in a subregion and the asymptotic soft physics sector. If you haven't heard much about that, it's not super crucial for this talk. And the main takeaway is that quantum reference frames will unify these different notions of entanglement and entropy that I mentioned here in all of these works. And they're going to be able to give us a systematic understanding of what do they mean. So this is the motivation. If you have any questions about it, you can ask now. If not, I'll proceed with probably the first question you have, which is, what are edge modes? So this is based on this work with Philip, Francesco, and Biliana, and is the first part of the talk, classical edge modes in the continuum. So the question is, what are edge modes? So let's start with free Maxwell theory, just to keep everything simple, so no interactions. And what is an edge mode? An edge mode is any non-local functional of the connection A. So our fundamental fields are given by the connection A, which is not gauge invariant, of course. But any non-local functional of A that transforms in this way under gauge transformations on the corner. So under gauge transformations, A transforms like this. If I have any field that transforms in this way, that's a valid edge mode. This is, what is this equation telling you? That this phi parametrizes the orbit of the gauge group. So edge modes, what are they? Reference frames for the corner gauge group. And as I said, any non-local functional works, so there's a whole set of possibilities. And a priori, none is better than the other. So an example that's particularly visual is a Wilson line anchored to the asymptotic boundary. So what do I have here is the same causal diamond I had before, but I've also drawn the spatial boundary of the universe, this B. And what I'm going to do is I'm going to construct a scalar field on this partial sigma surface at every point. And at every point, I build it by evaluating the value of the Wilson line that connects that point to some point on the asymptotic boundary. So it's some integral of A. And this integral, if you do a gauge transformation that has support on this corner, it transforms exactly like this. And this is going to be the main type of edge mode we will have in mind, just because it's pictorially more easy to understand. But any functional will do. And we're going to start introducing some nomenclature. So I'm going to call this an extrinsic edge mode. So we're going to distinguish between extrinsic and intrinsic. Extrinsic edge mode means, so it's a reference frame on the corner, it's an edge mode, and it's extrinsic with respect to the subregion, so it's built from the complement degrees of freedom, rather than the degrees of freedom that are already present in the subregion itself. So this is a complement-supported set of edge modes. This was introduced in this paper. And what does this edge mode allows us to do? It allows us to build a gauge-invariant subregion symplectic form. So we're classical. We just want to build a phase space with a symplectic form that is gauge-invariant, a symplectic form for the subregion degrees of freedom. And this allows us to do that. How does it do? Well, we start with a sort of kinematical subregional phase space. So this is the symplectic form. If you're not familiar with covariant phase space, this is just QHP. The star F is just the electric field. And so this runs over the spatial indices, AX, AY, AZ, and EX, EY, EZ. And so this is the conjugate pair of Maxwell theory, but it's kinematical because it's not gauge invariant. A transforms, this stays invariant, so the whole thing transforms. But so it's not gauge invariant, so it's not a valid phase space symplectic form for the subregion. But we can make a gauge invariant by adding this corner piece. So see, this is supported only on the corner, and it involves this edge mode or any such functional, and its conjugate is this is nothing but the perpendicular electric field on the corner. So E perpendicular the normal component perpendicular to partial sigma, and this composite symplectic form is gauge invariant because phi transforms in such a way that cancels the transformation of A. And so this is a kind of dressed subregion phase space. So we dress it with the reference frame, which was the edge mode. And I'm going to put this label X for extrinsic, so it's a extrinsically dressed symplectic form, as opposed to another type that's going to come up later. So this is exactly what just a classical level, what the reference frames would be used for. And as I said, this is gauge invariant, and this was what was introduced by Donnelly and Friedel in 2016 that studied the whole edge mode program. Now, yeah. Correct. Yes. And in fact, in this paper, that's what all they demanded. They just declared, let there be a field phi x on partial sigma that transforms like this. Then I build this, and it's gauge invariant. The question that then these people answered was, okay, where does this field come from? And this is an example. It's built from, so this is built from the kinematical data of the global theory. From the perspective of the subregion, it looks like a new field, but not from the perspective of the global theory. And this is an example that transforms appropriately and does the job that Donnelly and Friedel wanted. But for us, it's going to be very important to keep track of how this is built for the questions about entanglement entropy. Yes. Yeah. Right. So if you enlarge your region all the way to the asymptotic, you're going to recover the phase space of Maxwell theory on the full Minkowski space-time. So that's, it will be gauge invariant, and it will include some modes on hard photon modes and soft modes. And together, it will be a gauge invariant phase space. So this notion of having a corner piece is present both in the subregion and in the global theory. And they limit to each other, yes. So all we're doing here is addressing of a phase space and with a reference frame for the corner gauge group, which here is U1 at every point. And I'm going to introduce now the concept of a subregional Goldstone mode. So remember, the edge mode here is gauge covariant. Now the subregional Goldstone mode will be a gauge invariant mode on the corner. And how we're going to build this? Well, it turns out that if I take any such extrinsically dressed symplectic form like before, by dressing with some edge mode, then I can always decompose it into these two terms, and I'm going to tell you what these terms are. So this decomposition depends on some choice of another edge mode. So there's two edge modes involved. There's the original phi I started with, and there's a so-called phi tilde. And the phi tilde is an intrinsic edge mode, so it's built from degrees of freedom inside the region. So at this level of this equation here, I gave you an example of an extrinsic edge mode, but I could have done the same thing with a phi tilde here. So something built from the degrees of freedom already inside the region sigma, and built a so-called omega intrinsic. There will be different phase spaces because they'll have access to different observables. But the point is, anytime you dress extrinsically, the phase space factorizes between a gauge invariant bulk supported piece and the gauge invariant corner supported piece. So see here they have the difference of two frames. So this combination is gauge invariant. So in the sense, this is the physical corner mode pair, is this combination here. It's something that's gauge invariant and in principle measurable. Whereas the edge mode is a reference frame, it's not measurable. But this combination, the difference of these two, is measurable. And this is, so it's a gauge invariant bulk corner factorization. So this is a gauge invariant set of degrees of freedom entirely supported on sigma, the surface of the subregion, the partial Cauchy slice. And then there's the corner modes that are gauge invariant. And you see that the physical conjugate, so the gauge invariant conjugate to the corner electric flux, to the perpendicular electric field, is always a cross-boundary observable. Is always the difference between some intrinsic edge mode and an extrinsic edge mode. So the extrinsic is crucial. If you don't dress to an extrinsic edge mode, this piece just doesn't exist. You just have no corner modes. Yes. Right. Right. Yeah, you can do this. This is valid. You can proceed with the physics from here. So here, but in a sense, I would say that the extrinsic one is physically more potentially more interesting because, in a sense, you're dressing whatever system you are measuring to some, let's say, apparatus or something that's usually seen as outside of the system. It could be indeed a bulk or outside. For example, you could dress here. If I go back to this picture, I could dress my degrees of freedom. Let's say I have a shell of charged particles somewhere here. I could dress the subregion to the charged particle world lines. For example, I could also dress two charged particles inside. So it's a matter of choice, depends on what your setup is. I agree with you that the dressing intrinsically is valid, but you have access to less observables. And the reason we were interested in this is because in gravity, the extrinsic dressing is likely to be crucial, because here I just specify the subregion by just drawing it, but there I'm going to have to define it relative to something else. And the setup we have in mind is that you'd be defining it relative to some degrees of freedom outside. And in that sense, then the extrinsic dressing will be much more natural. But I agree with you that at this level, you could proceed with the intrinsic one. But you would actually miss some information about the entanglement entropies. Yeah, exactly. Yes. Yeah. Exactly. This ambiguity of which edge mode you add is exactly the same as the corner total derivative ambiguity for the spiral form. Yeah. So the Lagrangian doesn't tell you which edge mode to pick. It's the setup that will tell you. So the Goldstone mode, the takeaway point from this slide is that what people call Goldstone modes are nothing but relational observables. And they're in particular the difference of two edge modes or two frames. One that's extrinsic to the system, one that's intrinsic. So whenever you hear about Goldstone modes, this is really what's happening at the gauge invariant level. So it's the difference of two edge modes. Right. So because we have reference frames, you may wonder, okay, what is the role of frame reorientations, if they exist? And the frame reorientations are exactly going to give us physical symmetries. So people talk a lot about corner symmetries, which have to do with transformations of the corner modes. And they're physical to the gauge invariant. And this will be nothing other than frame reorientations. So what are these? They're just some non-degenerate flow of the phase space in which you shift the extrinsic edge mode by some function while keeping the connection fixed. So this is frame orientation. So you keep the system fixed and you change the reference. And associated to these frame orientations, there's an infinite set of corner charges. So for every function on the sphere, partial sigma, there's a charge that generates this transformation. And at the gauge invariant level, the only observable that it shifts is this Goldstone mode. So the Goldstone mode, that's why it's called the Goldstone mode, because it parametrizes the orbit of physical symmetries. And this is completely analogous to the asymptotic soft sector, where you have an infinite set of charges at infinity, and the Goldstone mode that parametrizes the orbit of those charges. Yes? So A is non-invariant, capital phi is non-invariant. But in that refactorization of the symplectic form, you end up with the gauge invariant corner mode, which is this Goldstone mode. So that the shift of the Goldstone mode is physical. Yeah. And this is not a gauge transformation, because A is being kept fixed and phi is changed. Gauge transformation would affect both of them. It's physical transformation, yes. Yeah. And the connection to the, I'm just going to quickly go over this because it's not the most crucial thing. I just wanted to take away that the connection with the asymptotic soft sector is even more precise than this, other than the fact, so there's already the same structures, but you can explicitly show by, if you take a particular type of edge mode and we compute what this Goldstone mode is, so curly phi is always Goldstone mode, you can explicitly relate it to the asymptotic, the data of the global theory, so it depends on some electric field on the surface and the soft mode and so on that live here. It doesn't matter. The point is that the reason it's useful to write this Goldstone mode observable in terms of global data is that then you know how to generate the frame orientations operationally. So for example, you can send some pulse of electromagnetic radiation that's like space-like separated from your region, and that will shift your Goldstone mode in this way. And from the perspective of the subregion, that will look like a physical corner symmetry. You can also do large gauge transformations, but these are not so operationally well justified. But this is kind of like hard photon mode. By hard, I just mean non-zero energy. So it's some wave packet of photons that is supported here on this cut, passes here, and from the perspective of the subregion, if you keep track of the observables associated to this phase space, it will look like a corner symmetry. But this part is just, maybe you can ponder about it at night. The crucial things were what are edge modes, how to dress the phase space, and there's some concept of Goldstone mode. And now we're going to go to the lattice and do everything quantum level, and then it's going to become just QRF application very directly, and you're going to see. Any questions on the previous part before I move on? Yeah. Mm-hmm. No, A is not physical, it's fixed. So you'll see, maybe in the quantum level it will ring a bell more. So this is the kinematical system degrees of freedom, and this is the reference, kinematical reference degrees of freedom. The frame orientation shifts the reference while keeping the system fixed. But on physical states, this will act like a physical symmetry. So classically, the statement that I'm making is that I'm looking at the flow of the gauge invariant symplectic form. At the quantum level, it will be a unitary transformation on the physical Hilbert space. Yeah. These ones, yes. They're conjugate to the electric field. They basically correspond to Wilson loops that cross the boundary. They'll be, yeah, it's a magnetic degree of freedom, yes. It's a magnetic degree of freedom. So maybe let's go to more familiar territory. So this is based on this work with Philip and Francesco. And we wanted to go quantum, and in the continuum there are all sorts of problems that we'll hopefully get to. But on the lattice we can do everything explicitly. So this will be QRF formalism on steroids. So let me just start first with the motivation for lattice gauge theory. So what is lattice gauge theory? So you have some lattice with links and vertices. And we're not going to have matter. We're going to be working with the general gauge group. So I'm going to be calling A the gluons. The gluon degrees of freedom are going to be living on the links. The links are oriented, so they have some, it's important if it's oriented to the left or right. On the vertices, there's nothing. If you have matter, the matter degrees of freedom will be on the vertices, but for now, let's not have that. And the gauge transformations will act on the vertices, and they can act from the right or from the left on the degrees of freedom on the link. And why do we care about lattice gauge theories, other than the fact we can carry out everything explicitly? Well, this will have can have applications to lattice QCD, which is a very important way of, the only way we know how to do QCD computations at low energies. Also, it might be closer to an experimental setup. Yeah, the fact we can carry out everything explicitly without UV divergences will be important for us. So the degrees of freedom are on these oriented edges. So we have the kinematical Hilbert space is a tensor product of an L2 over G for each link. And the so-called holonomy operator, so this is a Wilson line operator corresponding to this line, let's say, lives on the edge E. For each edge E, there's such an operator. And the gauge transformations act on the vertices, and as I said, they transform. The gauge parameter is independent for each vertex. You can pick whatever you want, and they transform from the left and right like this. So rho is some particular representation of the group G. So to each holonomy operator, there's a representation associated to it, and that's generic. And the group G is generic as long as it's compact. And we have our subregion is this shaded region here. We have partial sigma, which is again the cut, and we have the asymptotic boundary. And the gauge transformations, we call gauge transformations everything that has a non-trivial support on the vertices inside, but for example, a transformation on the vertex on the boundaries, physical transformation, so-called large gauge transformation. So we don't call those gauge transformations. And the generators of this left and right action are so-called left and right electric fields. They have Lie algebra indices, doesn't matter. But the reason physically why you have left and right electric fields is because the gluons carry electric charge. If you had the Abelian gauge theory, the left and the right electric fields would be the same, because on each link, the photon does not carry any charge. So the charge on the left and on the right is the same. But for non-Abelian gauge theories, that's not true. And okay, this is roughly the structure of lattice gauge theory. And yeah, we're going to have a physical Hilbert space of gauge invariant states of the global theory. And the key point of the talk will be to associate gauge invariant algebras to these subregion degrees of freedom dressed to different sets of edge modes and see what we can learn from there. Any questions about this lattice gauge theory setup? And I'm going to be working with generic G, but you could do something that's more realizable in the lab, like for example a Z2 gauge group and have some qubits and so on. That will also be, the results will be valid for that case as well. So it could be SU3, could be U1. So it's a discretized version of Maxwell theory. Could be qubits with a Z2 group. You can flip the qubits at each point individually and treat it as a gauge symmetry. So this has particular connections to, quantum error correcting codes and like toric codes and so on. Yeah. It's a model for many condensed matter systems. Yeah. Where you want some. Well, it depends what your Hamiltonian is, but yeah, you can cook up system interactions such that that is a gauge symmetry. Yeah. So, to this audience, I don't have to talk much about Page-Router's formalism, but let's just recap the basic ingredients and so that we can use them, always have those in mind when we generalize. At this level of analysis, I'm going to be working perspective neutral approach. So I have some kinematical Hilbert space with some reference and system degrees of freedom that I'm going to declare kinematically what they are. There's a gauge action that's going to act as a tensor product. That's the case here for lattice gauge theories. So it's not a simplification. That's actually the case. And the physical Hilbert space is the gauge invariant subspace of this. It's an actual projector here because it's a compact Lie group. And the projector takes this form. And the reference frame is going to be given by not only a set of a kinematical factor, but also specified by a set of generalized coherent states. So these are states of the frame that transform like this under the group, so they parameterize the group orbit. And we're going to generically allow for there to be some isotropy subgroup. So some transformations that leave the coherent states invariant. That's going to be the case, for example, for the intrinsic edge mode, as you're going to see. So, and of course, if such an isotropy subgroup exists, then it's what people call an incomplete frame. And in our setup, because every link had an L2 over G, the frames are going to be ideal. You could relax that. You can start with, we haven't done that, but you could consider a lattice gauge theory in which on the links you have a different representation of the group, some less reducible representation. And there you might go into non-ideal realm, but here for standard lattice gauge theory, this is ideal. That's going to simplify things a lot. Complete means there's no isotropy subgroup, so every transformation of the group changes the state of your reference. Incomplete means that there's some transformations that leave it invariant. So the Page-Wooter's conditioning map, which I'm going to be labeling while it's clearly R, is just the quantum gauge fixing. So gauge fixing, if you do it properly, it's doesn't change the physics. You have access to the same gauge invariant physics. And more concretely, this quantum gauge fixing induces an isomorphism between the physical Hilbert space and some subset of the system Hilbert space. So you see here that if your frame has an isotropy subgroup, then this will be a strict subspace of HS. For the case of a complete frame, this is identity operator, so it's the full system Hilbert space. But crucially, basically the quantum gauge fixing gives you an isomorphism between the system degrees of freedom and the physical Hilbert space. And this is what the inverse looks like if you care, the one that gives the bijection. And we're going to be interested in relational observables on the physical Hilbert space, so on physical states. So what do I mean by that? We can think of it in multiple ways, but for example, we can think of observables on this side of the map and map them to the physical Hilbert space. So what do? I take an observable here. So it's a system observable, Fs. I H-twirl it because I want it to act on the H-invariant subspace and keep me there. So in general, if I have an isotropy subgroup, it's only H-twirled observables that survive the map. And then I map it back to the physical Hilbert space by sandwiching these R's and R inverse, and I put this projector pi-phys here to make sure that whatever state I put in here, it projects it first to physical states. So that overall, I'm looking at the action of a relational observable on physical states. And why is this relational? Maybe it's easier on the next line, because it can show that this is equal to actual relational observable. So you take a system observable and you dress it to the frame with this G-twirl and acting on physical states. So because of the right-hand side, this is a relational observable. And because of this equality, the relational observables span the whole set of gauge invariant operators on the physical Hilbert space. That's an important result of these earlier works also that happened here. So we're going to be interested in relational observables acting on physical states, basically. And just to point out again that when a QRF has an isotropy group, then it can only see a coarse-grained system. So if you give me any system observable, it only sees the age-invariant version of it. It's a coarse-grained kind of QRF. Any questions about this? Yes. Yeah.
So when it's not anymore
Right.
protection pattern, of course, that's internal point of view.
Mhm.
It's in agreement with external point. Is this how you see this?
This is this step. So you have the gauge invariant Hilbert space. If the quantum gauge fixing is going to the frame perspective, and there, I'm just looking at the system indeed. You see, just a projected subspace of the system. But in general, if the frame had no H group, H isotropy group, to be the full system, and I just in the gauge fixed language, I just measure the system. The reason we're doing this step is because we want to work at the pre-gauge fixed language, so preconditioned, so that we know exactly what we are talking about, what kind of observables, gauge invariant observables we are looking at. But there's as long as we are careful not to get confused, there's no problem in working at this level. We just have to remember that this is a gauge fixed or conditioned description. But they're equivalent. The algebras are isomorphic. Mm-hmm. Right. Here we're still in this part we have HR tensor HS still. I haven't gone beyond it. So I only have like a kinematical R factor and a system factor. And in the case of the standard page routers, the group is, okay, it's not compact, but it's L2R. The group is R, the HR is L2R, the reference factor. It's ideal, it's complete, there's no, you can make incomplete clocks. You can make non-ideal clocks, but in the standard case, it's ideal incomplete. There's no isotropy average, nothing like that. And at the end of the day, you're just measuring the system without doing anything to it in the perspective of the clock. If you go to the gauge invariant level before gauge fixing, you just dress by G twirl, and you get your gauge invariant observable. That's relational between the system and the clock. A time. Yeah. Yeah, for example. Yeah. And if you were working with non-ideal clocks, you also have some kind of projector acting on the system, so it doesn't see the full system. But it's from a different, the projector is coming from a different source. Here is from isotropy group. There would be from non-zero overlap of clock states. In our case, it turns out to be enough to work with ideal, but okay. So let's go to the lattice, and we should always keep in mind the standard page routers, and then things will not be too complicated. So what we're gonna do is, well, now we have some notion of spatial locality. The region is here, the boundary is there. We know where each degree of freedom is. We're not doing gravity. So before in the mechanical model, there was no notion of spatial locality. Here we have. So we're going to have to build a frame at the point in which it's supposed to deparametrize the gauge orbit. So in particular, we're going to have to build a frame at each vertex of the boundary. And the total frame will be the tensor product of all of these frame degrees of freedom. So it parametrizes not a single gauge group, but gauge group tensor however many times it appears, however many vertices we have on the corner. But it's still a gauge group, but it's still compact, so you can still proceed. So the extrinsic frame is going to be kind of like in the classical picture, this set of like Wilson lines that connect the boundary, which is this green, to the asymptotic boundary, which is this purple line, curve. So you see these thickened red lines. So for each point on the boundary, there's a thickened red line that connects to the asymptotic boundary. And that builds a reference degree of freedom at this vertex, for the gauge group at that vertex. And it turns out that for these kind of frames, they're complete. And before I didn't tell you how to build the intrinsic frame, but here I'm going to give a concrete example. We're going to build the intrinsic frame from degrees of freedom of the region itself. There's many ways. We're going to pick a particular way for illustration. And it's going to turn out to be incomplete. So this picture is easier. So imagine your surface is a sphere, two-dimensional sphere. So what you do is you pick a point on a vertex on the sphere. Of course, it's tessellated by these triangulated by these triangles. not necessarily triangles, by the vertices and the edges on the surface. So you pick a vertex on the codimension 2 surface on the corner, you shoot out a tree that touches every vertex on the corner, and such that there's no loops. So you shoot out a tree, and from these Wilson lines, from this point to, let's say, this point, that builds a frame for this point. And you do so for every point on the tree. So it's a similar Wilson line construction, and you get an intrinsic frame for the vertices on the corner. This turns out to be incomplete because of the fact that this node is part of the corner as well. So there's a one copy of the group worth of isotropy. But still, both sets are built from Wilson lines. And one crucial point that you should have in mind is that I told you before that the kinematical Hilbert space is L2 over G for each link. And now I'm building a frame on vertices. So what I'm really doing is a refactorization of the kinematical Hilbert space before I proceed to the rest of the page, Ruther's formalism. So I'm just building composite Wilson lines. So let's say if you look here, originally I had an L2 over G tensor L2 over G, and I'm just gonna build 2 degrees of freedom. Again, 2 degrees of freedom. One is the Wilson line from here to here, and the other one is the Wilson line from here to here, by taking products of them. So it's a refactorization of these 2 factors into 2 new factors that are composite. And in that way, the factor that corresponds to the full Wilson line from the boundary to the subregional boundary gives me the reference frame factor that I'm going to take as my reference. I'm going to declare that to be HR. So this is a kind of picture you should have in mind. So you see, you redefine a GVI, which is the product of the G's from the previous factors that go all the way to the boundary. And you do the same for the extrinsic frame and for the intrinsic frame. So you're refactorizing your Hilbert space on the corner and your Hilbert space on the complement. Yes? Right. So, yeah, that's a good point. So, in principle, I could dress to things that are arbitrarily close to the boundary. We chose not to do it here for several reasons. One is this is easier to illustrate, and it connects to the soft physics. That was one of our motivations. However, we could do the same thing with, for example, dressing to some particle. We just declare there's some particle here. Let's say I introduce matter, and I dress everything to that, and that can be arbitrarily close to the region. But I agree with you that it seems a bit ad hoc at this level, because now I have access to non-local observables that go all the way to the asymptotics. But crucially, it's not all observables. It's only a small subset of them. But I agree that's a fair criticism. But you can do things that are more observationally motivated. You'll see, once we get to the final answer, you'll see maybe you're happy with you want to stick to the purely regional stuff, and you can do that. But there's still a value in doing this because of the hierarchy we're going to get at the end. Yeah. Yeah. And again, for gravity, I think this external dressing will be crucial, which is another motivation to go like that. Yes? Mm-hmm. So I don't know the full answer to that question. It's a great question. Classically, from what I described earlier, there were choices as well. There were choices as well of what is phi tilde, what is phi. And here you're seeing again, as you pointed out, I can pick different trees on the corner and I have different frames. it's an interesting question if for things like when I compute entanglement, entropy, and so on, if I go to the continuum, if the answers converge. We don't know the answer. I think that's a very interesting question. My gut feeling is that probably they do converge in some sense. At least when you go to the continuum, the answer will be divergent, but maybe the finite piece will be, like the universal piece of the entanglement entropy will be convergent for all of these possible choices. I don't know the answer. It's a great question, yes. For the extrinsic frames, I suspect they don't converge because they probe different things outside. For the intrinsic frame, I do have a feeling they might converge in some sense. But it's a great point you raise that you can pick different trees, and so this is a different refactorization kinematically, and you call a different thing your HR, and if you refactorize differently for a different tree, you call a different factor in HR, and they have overlap. In the extrinsic frame, you can kind of get by without making them overlap, but in the intrinsic frame case, they always overlap. So one intrinsic frame is built from kinematically is built from another intrinsic frame, and system degrees of freedom and so on. It's kind of like some repackaging. And that's gonna be important. Any other questions about this setup? So this is just how to build the frame schema. I think it's an important point also that here what we're really doing is kinematically build the reference degrees of freedom. We're not adding them by hand or saying just declaring they exist. We had some kinematical degrees of freedom given to us by the theory, and we're just building composite degrees of freedom. And you can do that, and I think this kind of mentality we should have also when we do quantum gravity problems. For example, building the clock from certain degrees of freedom and so on. Yeah. And I know what you mean. So, from what I'm going to tell you today, all are equally good. But that's maybe because we haven't named enough criteria. We're just, but for example, as you may be thinking as well, depending on what the global state is, there may be better or worse edge modes, or clocks in this case. So some refactorizations kinematically may be preferred if you want to describe the physics of in a given gauge invariant state or another gauge invariant state. They might minimize some parameter, something you might be interested in minimizing. Yeah. I agree. I agree with that spirit. Here, remember that here the group action was always as a tensor product. So the setup here does not deviate from page routers without interactions. They could, yeah. But in more generic setups, I agree this will become important. Yep. It's always incomplete. And in fact, for the extrinsic case, it's we don't have a proof of this, but I think it's only complete if you dress to the boundary. If you dress to anything else outside of your region, there will be some isotropy group as well. But for intrinsic frames, it's always incomplete. I think incomplete frames is just something that's the more natural thing to expect, that there's some coarse graining that your reference frame naturally implements on your system. It's coarse graining. I think they're both somehow implementing coarse graining. This one is, I have the set of observables, and some of them land on some orbit of some group, and the frame just sees the orbit as one, gives always the same answer for the whole orbit. So that's a coarse graining. Yeah, I never really understood what there is a subtle difference. Yeah, I see this as coarse graining. That for example, that's an example. Here it's infinite. Yes, this is it. Exactly. It's a different kind of. I think they're both implementing coarse grainings, but from different natures. Yes. Yeah. Here is if everything is ideal. Yes. This is a 1 hour talk, right? Or it's a 1 hour talk, or okay. So let me just describe the physical Hilbert space now from the perspective of this extrinsic frame, and we're going to see that it leads to some notion of factorization at the physical Hilbert space level. If you don't work in entanglement entropy and lattice gauge theories, you might not be so surprised, but usually there's a whole tension between gauge symmetry on the corner and factorization between inside and outside, and the QRF kind of tells you how to resolve that. So let's take a look at this equation. So what I'm taking here is the kinematical Hilbert space, but I have already implemented gauge transformation, like the projector of gauge transformations, at every vertex except the corner. So it's a almost physical Hilbert space, but not quite. It's kinematical only for gauge transformations on the corner. And it's already refactorized in the sense that I described before with these composite Wilson lines and so on. So you have, for example, here you have H sigma minus phi tilde. That means the Hilbert space for the sigma degrees of freedom, having removed the degrees of freedom for the intrinsic frame, and the superscript phys just tells you that they're already projected for all the gauge transformations inside except the corner. Similarly for the complement, so sigma bar is the complement. And then you have the reference frames that live on the corners now, on the vertices on the corner. This is like almost physical, but not quite. And this is the only one we care about because the frames are parametrizing gauge transformations on the corner, not inside or outside. So you take this kinematical Hilbert space, and the physical Hilbert space is just projecting on the corner with respect to the gauge, doing a group averaging, gauge averaging on the corner. And now the Page-Router's formalism follows identically, just a more complicated frame, but you can go to the perspective of the extrinsic frame by conditioning some orientation on this vertex, some orientation on that vertex, some orientation on that vertex, and so on. And what you're going to get, because the frame is ideal and complete, you're going to get HS. HS is everything else that's not the frame. So this is HR and this is HS, kinematically. So you just get HS. So you get some factorization that is inherited from the kinematical tensor product structure, but this is inherited crucially after that non-local refactorization. So it's not true that the physical Hilbert space factorizes between inside and outside just like that. It factorizes between inside and outside after having non-locally refactorized some amount of degrees of freedom. So it's kind of a non-local kinematical tensor product. It's a non-local tensor product structure, but from the perspective of the frame, it's local. That's the notion of locality that the frame sees. From the perspective of this set of Wilson lines, the locality of the universe looks like this. And if I give you a physical state that's entangled across these three factors, that entanglement is physical, is not gauge, because I'm already at the level of the physical Hilbert space, just gauge fixed. Whereas if you were doing something like this, which is what people call an extended Hilbert space, in which they embed physical states into basically this guy, the kinematical Hilbert space, and compute entanglement entropy there, that does not capture just physical entanglement. That captures entanglement between some gauge degrees of freedom as well. So you shouldn't do this. Whatever entanglement entropies we're going to talk about, they're always going to be at the level of a physical Hilbert space. So this part here, this combination, is all the degrees of freedom inside of this. The complement one is everything outside minus these thick lines. because there's this kind of non-local refactorization that I did before. So you're removing from this from sigma bar a non-local set a Wilson line here and a non-local Wilson line there, and so on. Sorry, say that again. It's not going to singlet or you're refactorizing. So you have two qubits, and you're refactorizing into two composite degrees of freedom that also look like qubits, as in they also can be up or down. But it's not up or down here, up or down here. It's some combination that's can be take value up or down, but it's delocalized. And another one that's also delocalized. But this is this is given to you by the choice of frame. From the frame perspective, it always looks like qubits. Just what the frame says, there's a qubit here. If you were to go back kinematically, it would be delocalized degree of freedom that still can be up or down. It's a frame-dependent notion of locality. And just to point out how the incompleteness plays a role, the intrinsic, if I want to the perspective of an intrinsic frame, it does not yield the factorization. So the intrinsic frame does not see factorization between inside and outside. That's because it's incomplete, so there's this projector acting on HS, so this is HS for the frame, for the intrinsic frame, and it's non-local projector, so it projects on a subspace of this that's entangled. So it doesn't, you cannot have factorized states from the perspective of the intrinsic frame, but you can from the perspective of the extrinsic frame. Notice that because you have factorization, there exist physical states that have zero entanglement between inside and outside from the perspective of the frame. I can pick a state that's factorized between this and this, and that from the perspective of the frame, it will say von Neumann entropy 0. And that's okay. Yes. If they do this, they are. Yeah. Yeah, and you've removed all gauge information already. Exactly. Exactly. Yeah, this is an isomorphism. If you don't know QRF at all, you would, if I give you a state on physical Hilbert space, you'll have to ask the question always of when I compute entanglement, I compute entanglement between what and what, right? So I have to make some partitions of what is my system, what is my complement. And there's many choices, and you're going to get different answers for the same state, depending on these choices. What the QRF tells you is that each frame perspective, edge mode perspective, gives you a notion of inside and outside, with respect to which you can compute that. You don't have to follow this. You can pick a different notion of inside and outside if you want. But crucially, you shouldn't pick something like this, because this notion of inside and outside includes gauge degrees of freedom. So in a sense, the possible factorizations of inside and outside are in a sense in one-to-one correspondence with the choices of edge modes of reference frames. That's what the reference frame gives you. It's whatever it is, yes. Yeah, and you can, for example, this is one solution, and I think it's actually the case that any factorization you get is in correspondence with some conditioning with respect to a complete ideal frame. I think if there are no complete ideal frames that exist at all that you can build, I think there's no notion of factorization you can get at the physical Hilbert space level. So this is, yeah. So I don't think there's a sharp proof of this. This is from playing around what it seems to me that whenever, because you can go backwards, right? Whenever you give me something, I can append a reference degree of freedom, do a pi phys on it, and I'm going to get the inverse of this map. Similarly, if I start here, I can do a conditioning, and I always get something like this. But this isomorphism to get a factorization and not a projected subspace requires idealness and completeness. If either of these fail, it's always a projected subspace, so you never get... I think the fact that this is an isomorphism tells you that tensor product structures on the physical Hilbert space are in one-to-one correspondence with conditionings with respect to ideal complete frames. Now, interestingly, there could be systems in which you give me the kinematical Hilbert space, and there's no way I can refactorize things such that I have a complete ideal frame, and then maybe that tells you something about not being to factorize the physical Hilbert space. That's my intuition, the way I feel like this works. I understand. Yeah, but here I think the setup is slightly different. We're always working in given a kinematical Hilbert space and a gauge group. There's no extra stuff. We're talking about pure states. We can talk about density matrices, but at the moment we're talking about pure states of the physical Hilbert space that you get from this kinematical Hilbert space with that gauge group. So that's the setup. We're not. But if you forget another degree of freedom for which you also have to impose the gauge constraint, then it will change the game completely. The set of states will be different. Okay. I'm going to skip corner symmetries. It's just frame reorientations as before. You act on the frame while keeping the system fixed, and this plays out the same as in the classical theory, and but it's okay. The only thing that you need to remember is that they exist. So if you have a extrinsic edge mode, there exists frame reorientation transformations. For example, the large gauge transformations or some other unitary that you act on the complement of the region outside that implements this, like those photon wave packets that I described earlier. So they exist. It's important that they exist for extrinsic edge modes. And they just reorient your frame at each vertex. And as again, you can reorient differently at each vertex. There's an infinite set of charges and so on. The intrinsic frame has no reorientations, but the extrinsic frame has. So now let's get to the main point of the talk, which is now we have all of these different edge modes, and what are the algebras of observables that we can cook up, and how are they related? So remember that the relational or dressed observables, they're just these G-twirl. You take a system observable and you pen to it this reference projector and the G-twirl it. And if you do this on the lattice, you get what you would expect pictorially. So by doing this procedure, you get all the gauge invariant observables you can have on the lattice. For example, you get Wilson loops, so things like this. Wilson lines that are anchored on the asymptotic boundary, so things like this. You get electric fields that are parallel transported to the boundary. For example, there's this electric field L here, the left one, and you parallel transport to the boundary. You get this composite observable. Quadratic combinations of electric fields like this. So take right electric field here, parallel transport to this point, and multiply by left. All these are gauge invariant observables, and all of them can be built from this G-twirling. And in particular, the Goldstone mode observables, you you just dress the extrinsic frame to the intrinsic frame, or vice versa. So the Goldstone mode observables, like before, remember, they're relational observables classically, they're relational observables quantumly as well. So what we're going to do now is we're going to take the subregional algebra and we're going to dress it to the extrinsic frame and get some gauge invariant algebra. So remember, here is a reminder of what the frame perspective of the physical Hilbert space looks like for the extrinsic frame. So what we do, remember the formula, to get the algebra of observables on the physical Hilbert space, it's enough to G-twirl and put a pi phys on the right. So what I'm doing is I take the algebra of all observables on this factor and this factor. So this is all the system observables. I append to it this projector, I G-twirl, and I put the pi phys on the right. And I'm going to get an algebra of gauge invariant observables acting on physical states. This acting on physical states at the end is important for the statements that follow. In particular, what you get here is the so-called type 1 factor. I mean, it doesn't type 1 just because we were working with mechanical systems. It's not a continuum theory. But crucially, it's a factor, meaning it doesn't have a center. And that's going to be important later on. If you didn't put this projector here, then you wouldn't have a factor structure. Mm-hmm. Mm-hmm. Yeah. It would not be necessary, yes. But as far as I understand things, because we are working with the gauge symmetry, we have to do this step. We're only so that we basically we just choose to evaluate these observables on gauge invariant states. That's the mindset we have in this talk. You can ask different questions, but yeah. Mm-hmm. And you can also address to the intrinsic frame. So it's a slightly different notion. So here you're addressing the full subregion to the extrinsic frame. Here you're addressing, because the frame is intrinsic, you're addressing the subregion minus the frame. So we're having removed that tree on the corner, addressing that to the frame. You don't address the frame to itself. So it's the same type of thing that you do. But now the only thing is that the algebra of the system observables have to be H-twirled, where H is the isotopic group. So because of this H-twirl, it's not a factor. So it has a sector structure with respect to the isotropy group. And these are all both gauge invariant algebras. They're subalgebras of the bounded operators on the physical Hilbert space, of all the possible gauge invariant operators. So this is kind of the relational algebras, dressed to extrinsic frame or dressed to intrinsic frame. There's another type of algebra that's of interest, and we're going to put them all together in the end, which is a so-called electric center algebra, which is closer to what Czeslaw was talking about. This is the most liked algebra in the literature on lattice gauge theories. It has all sorts of nice properties. And physically, what is happening here? We have the algebra of subregion dressed to the extrinsic edge mode. And as I mentioned before, there's these frame orientations, which are physical symmetries. And they just take an observable here and they map it to another gauge invariant observable. So it's an automorphism on the algebra. And now the question is, if we are ignorant about the observable that keeps track of this physical transformations, then we're going to have access to a coarser algebra. And how do we implement this coarse graining? We implement this coarse graining by G-twirling over that physical symmetry. So you take all the observables that the edge mode sees, all the relational observables, but then you are ignorant about these symmetry transformations, or the Goldstone mode, so to speak. You just average over those orbits. So you get a coarse-grained algebra, which is how we're going to define this electric center algebra. And why is it called electric center? And before, let me just point out, this is just an average over frame orientations. We're just declaring that in the lab we don't have access to measuring what the frame orientation is. Not frame orientation, we don't have access to the frame orientation transformations. And it's an electric center because the G-twirl introduces a non-trivial center, and the center is given by the Casimir operators for the group generated by the symmetry generators here. So the electric flux is the generator of these physical transformations. So the non-trivial center is given by the quadratic combinations of electric field at each corner, so the Casimirs. And this leads to the notion of charge sectors. So when you diagonalize in the basis of the center of the algebra, all the operators are block diagonal. And you can see this for density matrices. So you start with some density matrix on the original algebra. So you have a global physical state. And this is a subalgebra of the global algebra. So on this subalgebra, you think, what is the density matrix that belongs to this subalgebra that gives me equivalent results to the global state? So it's in the basis of these operators, it has diagonal components, but also off-diagonal components. Now you act with the G-twirl operator, and it basically erases everything that's off-diagonal, and it keeps only the block diagonal piece. So this is a density matrix on this algebra. This is a density matrix on the electric center algebra after having performed G-twirling. So in this basis, diagonalizing the corner center operators or Casimir operators, the twirl decoheres the density matrix. So you can have some coherence across sectors here, but then you do the G-twirl, you get completely decohered, and your density matrix only lives on the block diagonal components. And this will be important that this is a CPTP map as well. So usually in the literature of lattice gauge theories and entanglement, people start already here. They think of density matrices on the electric center algebra, and they declare from the beginning is decohered across sectors. But they get here by doing by not working fully gauge invariantly. They work with this extended Hilbert space that I was talking about earlier, that doesn't capture only physical entanglement. One thing I don't quite understand is how that non-gauge invariant step miraculously lands you on a gauge invariant answer. But here I think we gave a nice interpretation of where this algebra comes from the perspective of these relational algebras. Yeah. Yeah, okay. Thanks for raising that question, because maybe I was too quick here. Let me just go back to this equation here. Here we're doing a G-twirl with respect to the gauge group, and there we're projecting on the gauge invariant subspace, because this is you want to obtain gauge invariant operators on gauge invariant states. Here, it's a different symbol. It's a G-twirl over a physical symmetry, not gauge symmetry. The physical symmetry is the frame orientations. And we're not projecting here, because it's not a gauge symmetry, so I can have states that have non-zero charge. So this G-twirling is not coming because we want gauge invariant observables. That we already have done. This G-twirling is coming because I'm ignorant about the parameter, the physical parameter that parametrizes this symmetry. I think the standard clock page routers is too simple to see. I think you'll just get something trivial at the end if you do that. Yeah, I think it's maybe you may end up with nothing in the end there. Well, the physical symmetries there are the clock reorientations, when you shift the clock and keep the system fixed. So yeah, different, yes. But I think in that case you just end up with a trivial answer because you don't have enough degrees of freedom. But that's what you would be doing there. Here it's because you have many degrees of freedom and your frame is only for the corner. The answer is non-trivial. There's something non-trivial happening, yes. You don't get a trivial algebra, you get some, yeah. Mhm. Yeah. 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 So thanks for that question. So structurally they look very similar because the frame orientation group on the corner is isomorphic to the gauge group on the corner, happens to be the case. But physically there is really different procedures. So the first one of the G-twirl of the gauge group is the one that gives you the gauge invariant observable. So that just tells you, okay, my observable, I measure Wilson loops and this particular parallel transported electric field and so on, and you have the set of all gauge invariant observables. Then you say, the second step is, I cannot distinguish this observable from this observable in my lab just because I'm insensitive to this transformation. But it's physical transformation between gauge invariant observables. And so there's a whole orbit of a symmetry that you just happen to not measure. So you'll just assign the same values to all of these observables along this orbit. But it's physical observables, all of them. And this is a physical symmetry orbit. So that's what this G-twirl is doing. It's just you just have some coarse-grained glasses when you look at your system, and you just don't see the difference between an orbit of gauge invariant observables. But they're all gauge invariant already. No, but it's not gauge. It's not gauge. Oh, each edge mode, each reference frame has access to all of these. Yeah. The next slide will connect exactly to that. But I see it like, okay, the first step is I tell you what are the possible observables I could measure. And then the next step is kind of an operational one. I say, actually, I don't have enough resolution to measure this orbit with my apparatus. So I don't see that. This is actually, I really think it's a coarse graining, yes. You can, yeah. Until this slide, you didn't have to, it's perfect, I agree. This algebra is perfectly legit. There's nothing wrong with it. all we are wanting to do here is understand what is the relation between the electric center algebra that's usually in the literature and our algebras, and this is the step you have to do. Now, depends on your setup if you are justified to do this or not, if you want to do it or not, but they're related in this way. And maybe this will also connect to this discussion. I'm maybe 2 slides away from the end. The question of what the different edge modes agree on. So we can see that this G twirl will be related to a sort of intersection of these relational algebras. So let me just point out that there's in QRF there's this notion of subsystem relativity that you're probably familiar with. That for the same system, different frames associate different algebras, different gauge invariant algebras, because they address the same system to frame 1 or frame 2. You get different observables. So there's some intersection usually between these algebras that is non-trivial, but it's not the full algebra because they have non-trivial overlap. So they're not exactly the same algebra. But the one thing that is interesting is that that electric center algebra from before, that was obtained by G twirl of any one of these, can also be obtained by intersecting these. So you take the different relational algebras with respect to different frames. Hmm.
But it's interesting that you can get also averaging, which might be understood as totally coarse grain. Like
Yeah.
what remains if I really very much coarse grain everything.
Yeah. Somehow this intersection is related to coarse graining in this case of the extrinsic. Yeah.
This remains for me a question. I don't know when it's locally accessible. It's not feasible only through communications.
I feel that if it's all relation, you need communication. If you say you can measure all gauge invariant, you can access it even in just one reference.
Yeah, that's why I know it's.
It's like the extra particle for the other reference frame because it's in the gauge invariant space, but it's not relational, so he cannot access. But when he patching things together, he get this
But it's
information.
intersection. I'm not
It's
sure.
intersection, yeah, yeah.
Yeah, it's not a union, it's an intersection.
Sounds like it's
Really locally available.
yeah. This is the relational part.
I don't have any comment on the extra particle. Yeah. Yes.
Quickly come back to the thing, the second symmetry you asked before, because all of these maybe I'm thinking too much in to the spatial or orientation case, so with angular momentum
Mm.
translations. But like the whole matter of asking for gauge transformations for for reference frames is that you claim that, for example, a translation inside space is unphysical because actually, if you really translate everything, you will not see any change in your experiment. So everything, what really matters are just distances. And I understand that you can extend this concept to, I mean, two fields that the only important physical thing is it's not if they both in a way have a instantaneous gauge transformation, but only the relational
Mhm.
I would say information between the field you want to measure, so what's inside, and the field, the reference field. Okay. So, but if I think about this in the translational case, I have that if I move these two, okay, rigidly, I will not see any physical differences. But if I do this, I will, okay? But actually, I feel that the second symmetry you're asking for is this symmetry, but is not always there. I mean,
Yeah.
and so you get what I mean? Like, it's just asking for a Hamiltonian which is symmetric, but that's not, I mean, not trivial to ask. Sometimes it happens, sometimes it doesn't.
Yeah.
And so I really don't understand the second symmetry. I mean, I understand that if you want to treat free things, it may work. But in
So
general,
let me make a.
but yeah, sorry, if this is the case, then I didn't understand why it is useful to do this second step.
Mhm. So maybe first comment on terminology. When I say physical symmetry, I mean it's an operator that commutes to the gauge transformations. Not all states will satisfy the symmetry. Like if I have a translation invariant theory, having the table here breaks the symmetry. It's a state that breaks the symmetry, right? So it's not as indeed, I don't have to do the step of averaging. You'll have to give me an operational reason to do it. The point I want to make here is that they are related via that. They happen to be related via that coarse graining over that physical symmetry. But I. No, you always, it's always coarse graining. If you do the G, you always decohere. The, so the G twirl coarse grains. Now, whether you want to do the G twirl or not, it's a different. And coming back to your point about the translations, doing the G twirl of this physical symmetry is basically restrict yourself to a smaller set of observables. And if you, such that if you only measure those, you cannot tell the difference between these two states. But if you had access to more observables, like the observables here, then you can tell the difference between having shifted that or not having shifted that. So taking the intersection also lands you on that. Maybe another way of defining this electric center algebra is, that's why I put a definition here. We can just call it as the algebra that all extrinsic edge modes agree on in terms of observables. And that is useful because definition because it parallels the next one, which is if I take the intersection of all intrinsic algebras, intrinsically dressed algebras, then I'm going to get something as well, some other algebra, which I'm calling a AM. This you can show that it has a non-trivial center as well, like the electric center one. But the center is not given by the corner electric flux, it's given by the magnetic fields on the corner. So these Wilson loops, when I say Wilson loops on the corner, they're really measuring the magnetic flux on the corner. That's why it's a magnetic center. And there's also some electric part on the center. So the center is generated by both these sets of operators, but because of the fact there's a magnetic center, people call it the magnetic center algebra. So this is another algebra that appears in the literature on entanglement, entropy, and lattice gauge theories. People prefer this one, but they also like this one. So you can say a definition of magnetic center algebra is that it's an algebra that all intrinsic edge modes agree on. And this definition is goes beyond what people knew. People only knew how to define it for finite non-Abelian groups in 2+1 dimensions, whereas our definition works for any group and any dimensions. And I feel like it really captures what's going on, what these algebras really mean. Now, as pointed out before, this happens to be also given by the G twirl of a physical corner symmetry group. This is not always given by a G twirl. So the G twirl is not, interestingly, not always related to intersections. There are some cases in which this is also related to a G twirl, but not for generic groups. There's a notion of this speculative that somehow the intersection has might be a proxy for averaging over the QRFs. So I have some algebra, some observables that reference measures, the observables that reference measures, and so on. And if I were to average over what the reference is that I pick, the intersection in some sense is doing that. It's giving me the observables that I'm left over after averaging over that. So all the observables they agree on. So okay, last slide, and then I'll let you go. There's a hierarchy of algebras that I described. So if we start with the extrinsically dressed algebra and we take the intersection of these, you get the electric center algebra. Then the intrinsically dressed algebras, they're also a subset of these, you can show that. And if you intersect these, you get the magnetic center one. These ones are the relational algebras. They depend on the frame. Whereas these ones are QRF independent. By the very definition that they are intersection of overall QRFs, they're QRF independent. So the algebras that people care about usually, the nice ones, so to speak, they're the QRF independent ones, which is interesting. We weren't expecting that at the beginning. And because you have a hierarchy of algebras, you also have a hierarchy of relative entropy. As you do CPTP maps to go from one to the other, your relative entropy decreases. More interestingly, there's also a von Neumann entropy hierarchy that doesn't go across the whole thing, but for example, from here to here, there's always this inequality happening, and this is precisely because to go from this algebra to this algebra, you can also G-twirl. So the G-twirling, because it always decoheres across the sectors, it can only increase your von Neumann entropy of your density matrix. So if I start with the density matrix on this algebra here, and I compute a von Neumann entropy, I get something. If I do the G-twirl to get the density matrix on the electric center algebra and I compute von Neumann entropy, I get something strictly bigger. Could be equal, but at least bigger, not smaller. And for the magnetic algebra, you can also do a similar thing for the cases in which you can write this step as a G-twirl, which is not always. That's why there's an asterisk here. So it's really a coarse graining because it increases your uncertainty. So the level of von Neumann entropy, it really acts like a coarse graining. And okay, I'll just flash this slide, like what the von Neumann entropy looks like for if I compute it on different algebras. And basically, when there is a center, like this case, in this case, there's a Shannon entropy piece, because there's a classical probability distribution across sectors. And there's a piece that comes from the ERAP uncertainty in ERAP space as well. When you have no center, the von Neumann entropy is just pure entanglement, distillable entropy, and so on. Let me skip all of this. It's not much, but let me go to the conclusion slide. So what did I talk to you about today? So we defined the notion of subregional Goldstone mode, the gauge invariant observable that lives on the corner. I briefly touched upon this relationship to asymptotic sector. We talked about the physical Hilbert space factorization on the lattice. And the most important part was this whole notion of relational algebras and how they are related, which we think is new. And I didn't talk at all about, I knew I was not going to reach the continuum, that's why it's already in a different color. And future directions that would follow from this, that I think may be interesting to the group as well. Main motivation for us to study edge modes was to go to gravity. And there's this whole corner program that has these people and many, many, many more about these corner symmetry transformations when you have a region of space. There's not a very clear understanding of the edge modes in that case. So we feel like we'd like to import some of our understanding to that. Observers in perturbative quantum gravity would also be interesting. For example, just to point out that these works that in which they dress the QFT degrees of freedom to some world line, that's in spirit of this kind of algebra of dressing the subregion to the extrinsic edge mode. So we'd like to understand our hierarchy of entropies and so on. How does it interplay with this kind of toy models? We'd like to understand what this Goldstone mode sector is actually, what is actually mean from an operational point of view. So this gauge invariant, yes, but how do we have access to it? And there's some people who are interested in computing the two-point function of the conjugate to the Goldstone mode, which is a local observable. So it would be interesting to understand that a bit more. Because this is Catherine Zurich. This is, it's a different person maybe. Sorry. Yeah. Importantly, I think an important step would be to extend this to non-ideal edge modes. See how the finite resolution interplays with the whole structure that followed, in particular for the algebras and the entropies. And I think one thing that I'm very interested in is this notion of averaging over QRFs. And I think this is an important question to formalize and understand what it means, and to kind of perform this intersection of algebras in a systematic way. And yeah, I'm gonna leave it at that. Thank you for your extended attention.
Just one, two, brief one. Yeah.
Okay, so maybe this is not probably is not really mathematically that well posed, but I was wondering now this is all in a treatment of obviously of subregions of space. But what if we want to push this boundary to the whole universe at some point? I mean, intuitively, I would imagine that then the extrinsic algebras would mean less, would become trivial. So then I ask myself, what happens to the electric center and magnetic center algebras? Is there a situation where due to the gauge group or this limit, they become trivial as well? So there's no common information between QRFs?
So in the case of Maxwell theory, so as I pointed out earlier, if you take this limit of the region going to infinity, you recover the global algebras that you can have. And also in the global theory, you can have multiple algebras depending on what observables you keep track of. The electric center algebra is, I agree that the extrinsically dressed algebra loses meaning because you don't have any more kinematical degrees of freedom to dress to outside. The electric center algebra is also there in the global theory of Maxwell theory. It's the center is given by the global asymptotic charge, the charge at square plus minus, so the large gauge charge. You have these sectors there as well. Now, the Goldstone mode that we have here will be in the limit will map to the Goldstone mode of the global theory, and the Goldstone mode is charged, so it can move you across these charge sectors. But if you tell me I cannot measure the Goldstone mode, which you may want to say that, then you are again in this G-twirled version, electric center algebra, and you have these sectors. And the magnetic center algebra is also present there. You also have you can also have magnetic charge sectors in Maxwell theory, but usually we don't consider that because they're dynamic. The dynamics of QED cannot map you from one sector to another. So if you start in one, you're always there. So you just declare you're in the zero magnetic charge sector. Whereas the electric charge sectors, you can move dynamically if you have matter between one and the other. So these algebras, they all exist, even in the infinite limit. I think that this hierarchy would stand. But I think the subregion physics is more interesting than the global one.
Yeah, but okay. So in the electromagnetic case, this is. But if I ask for more symmetry, like for a group that is heavier, like I don't know. Like
Yeah, you'll have. I mean, on the
point where there's no freedom left in this interception. But maybe there's no really mathematical way of.
You mean if?
Yeah, that these central algebras, there is no block diagonal for it. It's
just one sector. I think, for example, in this case of Page-Witter's clock, that will be the case. If it's too simple, the system, I think you can get to that. Yeah, exactly. But if you have enough degrees of freedom, in general, it's not. This works for non-Abelian groups, any group that's compact. So you can go arbitrarily big in the group, and this will hold.
Okay.
Let's conclude. You are still around today, so
yeah.
Thank you very much once more. Yeah.
You're welcome.